Hello, my name is Liam Barber and I am a clinical exercise physiology student at the University of New England. In this video, we will explore the speed-accuracy trade-off in physical activity. I will first give a brief explanation about what the speed-accuracy trade-off is, followed by presenting the details of 3 separate experiments conducted based upon varying aspects of the occurrence. Finally, I shall concisely discuss both the implications of this information, as well as other ways in which speed-accuracy trade-off is investigated. Over a lifetime, every individual undergoes near constant physical activity. Every action requires the use of motor skills we have developed and enhanced throughout our experiences. The way we utilize these motor skills may vary dependent on our goal. Both speed and accuracy are potential variables that we constantly manipulate in order to perform an action in a specific way. In the study of motor control and physical performance, it has been shown that both speed and accuracy must be balanced out in order to perform a task to the optimal level. This creates the speed-accuracy trade-off. This is the concept that for accuracy to be emphasized, speed must be decreased, and vice versa. This is a balance that is worked out countless times a day subconsciously. Everything from accurately hitting a light switch to picking up a single grape from a bunch requires the increase in time taken to achieve the accuracy that the task calls for. The first experiment investigated how the required accuracy of a throwing task affected the speed of the throw. The participants were asked to complete 10 underarm throws of a tennis ball at 3 different sized targets. The first target was simply a wall. The second target was a paper bullseye that was stuck to the wall. The third and final target was to hit the innermost rings of the bullseye. For 10 trials, at each of the targets were recorded as a score out of 10, as well as the time taken to throw the ball at the target. The participants tried to complete every throw quickly, but the emphasis of the task was on accuracy. The results from this throwing task conveyed one obvious finding, which was that as the required accuracy increased, fewer throws hit the target. This was, however, accompanied by a small decrease in the throwing speed. Although this experiment did not completely convey the decrease in speed to increase accuracy as per the trade-off, it did demonstrate how failing to manipulate the speed variable in a motor skill led to the failure of the task due to inadequate accuracy. This demonstrates the requirement for the speed-accuracy trade-off when completing a motor task, rather than the occurrence itself. The second experiment relied on the underlying assumption that an individual is noticeably less capable with their non-dominant hand. The task involved using the Purdue pegboard task. This is an assembly task that involves placing key-shaped pegs into the holes in a board in the correct angle to fit. For the purpose of this experiment, the participants were required to fill the board from left to right along each row, arranging each peg to the next hole, rather than placing the peg into a hole that happened to fit the direction it was picked up in. This detail emphasized the need for the same accuracy and fine motor control for each hole. Each participant completed the task 9 times, with the aim of placing as many pegs into the board as possible in 20 seconds. The task was completed under 3 separate conditions, for which 3 trials were completed. These were using both hands, using only the dominant hand, and using only the non-dominant hand. For each trial, the number of pegs placed was recorded as a score. The results matched the explanation of the speed-accuracy trade-off. Although the difference between dominant and non-dominant hands was not large, the trend did display that the condition that was theoretically the most difficult, and as such required more accuracy, scored the lowest. This lowered score indicates the decrease in the speed that the task was completed. Using both hands for the task was assumed to be the easiest condition, and the increased average score suggests that it was able to be completed the fastest while maintaining the required level of accuracy. This may suggest that training a particular motor skill, in this situation the dominance of one hand over another, can lead to an altered balance in the speed-accuracy trade-off due to the required accuracy being more easily achieved. The final experiment involved bimanual control. This is when we try to execute 2 different movements at the same time. A simple example in everyday life would be the way that both hands move differently when trying to tie a shoelace. This experiment investigated how speed impacts the completion of a motor task in 2 different movements of both index fingers. The 2 movements can be described as demonstrating in-phase coordination and anti-phase coordination. Each of the 2 movements were completed at a slow and fast pace for 20 seconds. The trial was scored at however many seconds could be completed without the participant losing timing. The results suggested that speed was only a significant factor for the anti-phase movement, while there was only a very minor decrease in the average time the in-phase movement could be performed for at a higher speed. The trade-off is better conveyed in the other task. The fact that the increased speed cannot be maintained along with coordination demonstrates how the accuracy of the motor task was compromised when the 2 variables were imbalanced. All 3 experiments were able to demonstrate the fact that speed and accuracy must be balanced at a point to produce optimal performance. This is not rare, considering that the concept of decreasing speed to increase accuracy has been explained in the mathematical law known as Fitts' law. This law is often generalized when explaining in the context of motor control and sports performance. A large portion of the general knowledge on the topic of speed-accuracy trade-off is related to sports performance. Considering that this approach can be used to find the optimal level for physical performance, variables that affect motor performance, such as both speed and accuracy, are obviously focused upon. Examples of this are the balance between speed and accuracy when taking a shot in soccer, or when throwing a dart. When accuracy is more important, the speed of the kick or the throw decreases. However, because the concept of a speed-accuracy trade-off is quite well understood, many recent studies are not about whether it is or is not present, but rather the way in which it works. For example, the paper by Van den Tiller and Ettimer aims to investigate whether experience has an effect on the nature of speed-accuracy trade-off. Another study from Duthill, Wagenmakers, Vizier, and Van der Maas references several different models for the speed-accuracy trade-off. The future of research on this topic is more about gaining a deeper understanding of the mechanics and uses of the speed-accuracy trade-off. In conclusion, the requirements of either speed or accuracy in any given task will result in a trade-off between the two, resulting in a balance that will aim to provide optimal performance. The 3 experiments all supported this occurrence, and although this trade-off is often utilized in a sporting context, much of the recent research is focused upon understanding it more deeply, rather than how to practically implement it into a specific motor task. Thank you.